In this video, we're going to talk about one of the two rules we use to calculate the probability for more complex events. We're going to start with the addition rule. The probability of two or more events is calculated using addition rules. In general, when you see the keyword "or" in a probability problem, that means we're using an addition rule. It means to add. So the addition rule is for two events A and B, the probability of A or B happening is equal to the probability of A happening plus the probability of B happening minus the probability that an event that both is A and B happens. So let's look at why we need to subtract off that P, A, and B. So what I have here, this picture with a square and some circles, is called a Venn diagram. And we're going to look at a Venn diagram for rolling two dice. And we're going to let event A be rolling an even number. And we're going to let event B be rolling a prime number. And I know that rolling a six-sided dice, my options are the numbers 1 through 6. 1 through 6. So I need to place those numbers in the table where they go. So I'm going to go down my list 1 through 6. 1 is not even. It's not divisible by 2. It's also not prime. Prime numbers have exactly two factors, one in themselves. 1 only has one factor, itself. So 1 is an oddball who's going to sit out here. Now we're going to start going through the rest of the list. Our next number is 2. 2 is even. It's divisible by itself. It's also prime because the only factors are 1 and 2. So it lives here in the overlap. Our next number is 3. It's not even, but it is prime. Its only factors are 1 in itself. 4 is even, but not prime, because 2 and 2 are factors. 5 is prime, but not even. And 6 is even, but not prime. So this Venn diagram is a table of all possible outcomes. I can see the numbers that are prime, the numbers that are even, the numbers that are both, and the numbers that are neither. And that's what a Venn diagram was. We're going to look at it again later. And there's something to notice about our formula. When I calculate PA, in this case A is even, that's this whole circle. When I go to calculate PB, which is prime numbers, that's this whole circle. Meaning 2 got counted twice. It got counted with the evens and then with the primes. I need to subtract off that double count. And that's what this is doing. It's removing the fact that I counted the 2 twice. If an event, go back up here, is mutually exclusive, meaning in a Venn diagram, the circles don't touch. There's no events in common. I don't have to worry about that subtracting the overlap. So if A and B are mutually exclusive, A and B is 0, and we're just adding. This is one way to check that two events are mutually exclusive. If the probability of both happening is 0, that tells me they meet the requirement for mutually exclusive. So this works both ways. If I know they're mutually exclusive, P, A, and B is 0. If I know P, A, and B is 0, they must be mutually exclusive. So let's go ahead and do some examples so we can practice. First example says the probability that John will drive to school is 0.37. The probability that he will ride with friends is 0.23. And the probability that his parents will take him is 0.4. He is not allowed to have passengers in the car when he is driving. What is the probability that John will have company on the way to school? So looking at the three outcomes, we have, where are we looking? Get my colored pen out here. So John drives to school, and we know that he does that alone, so no company. Probability he will ride with friends is 0.23, that is company. And then that his parents will drive him would also be with company. His parents are in the car. He might have guests in the car. So when I go to do P company, I'm looking at P friends or P parents. I don't have to worry about his driving to school because we're told that he can't drive with other people in the car. So he's either riding with friends or he's riding with his parents, and there isn't any overlap between these categories. So I know to calculate that probability, I'm adding the probability that he rides with friends and the probability that his parents take him. And that gives us 0.63. Happy face. So there's a 63% chance that John has company on his way to school. Another thing to notice, if we add those three numbers, they add to 1. So this represents all of the options for John with no overlap, because 0.4 plus 0.23 is 0.63. 0.63 plus 0.37 is 1. So he has to be in one of these categories, and there's no overlap. Let's try another one that's a little less confusing. So this one says, a meeting room in a dormitory. There are 8 bags of potato chips, 5 bags of popcorn, 2 bags of pretzels, and 1 bag of cheese puffs. If a student selects one bag at random, find the probability that the bag of potato chips, the bag is a bag of potato chips or a bag of pretzels. So I'm going to write my probability statement. I want potat or pretzel. I know or means add, so I'm going to have to do P potat plus P pretzel, and then for that last chunk I'm going to ask, is there any overlap? And looking at the outcomes, there's potato chips, popcorn, pretzels, and cheese puffs. None of that overlaps. It doesn't say that any of the bags are potato chips and pretzels. So it's one of those 4 by itself, meaning there's no overlap, so I don't have to worry about subtracting any overlap. We do have to do a little bit more work for those individual probabilities. We're going to have to set up their probability fractions. So looking at the word problem, I have 8 bags of potato chips, 5 of popcorn, 2 of pretzels, and 1 of cheese puffs. So I'm drawing from a selection of 16 bags of snacks. So the denominator for both of these is 16. 8 of them are potato chips, and 2 of them are pretzels. So that's going to give me 10 over 16. And I can reduce that. Those are both even numbers. That's going to give me 5 over 8, or, oops, 0.625. So there is a 62.5% chance if I randomly stick my hand in the snack drawer, I'm going to grab a bag that's either potato chips or pretzels. Okay, let's try another one. So this one says the number of multiple births in the United States for a recent year indicated that there were 128,665 sets of twins, 7,110 sets of triplets, 468 sets of quadruplets, and 85 sets of quintuplets. Choose one set of siblings at random. Find the probability that it represented more than 2 babies. Whew. So, first thing I need to do is I need to figure out how many sets of siblings we have. Because I know that that's going to be the bottom of any probability fractions. So let's go ahead and add the sets. 128,665 sets of twins, 7,110 sets of triplets, 468 sets of quadruplets, 85 sets of quintuplets. So we have 136,328 sets of siblings. And finding the probability that it represents more than 2, in this case, more than 2 means 3 or 4 or 5. Because I only have 4 options: twins, triplets, quadruplets, quintuplets. So more than 2 is 3, 4, or 5. So I know that P more than 2 is going to be P, whoops, try that again, P3 plus P4 plus P5. And you'll notice I'm not subtracting off any overlap, because I cannot be both a quintuplet and a triplet at the same time. I'm one or the other. So there's no overlap here. So I'm going to set up our probability fractions. I know that there are 136,328 sets of siblings, so that forms the denominator of my probability fraction. And then for the numerators, for triplets, 7,110, quadruplets, 468, and quintuplets is 85. So we're going to add those. Denominators are same, we're just going to add the numerators. And we get 7,663. And in decimal form, that's going to be that number divided by that number. And that gives us 0.0562. So from this set of multiple births in a recent year, only 5.62% of them represented more than 2 babies, meaning twins were by far the most likely outcome. Okay, next one says find the probability that represented quads or quints. So P4 or 5. So using our addition rule, that's going to be P4 plus P5. And then I have to consider overlap. I'm either a quad or a quint. Those are mutually exclusive, so I don't have to worry about the overlap at the end of my equation. And we already did those fractions. Those fractions are right here. We know the probability of being a quint is 468 out of the total, and the probability of being a, sorry, that was a quad, and a quint is 85 out of that. So that's going to give us 553 out of the 1,036, 328. And that is a mouthful. Ooh, and that's super tiny, 0.041, which is 0.41%. 0.41%. So I can see from the last example, twins were the bulk. The next chunk must be triplets, because quints and quads are hardly anything, less than 1%, less than 0.5%. And now for a tricky question. It says, now choose one baby from these multiple births. What is the probability that the baby was a triplet? Ooh. So notice we switched from all of these that were talking about sets of siblings, right? More than two babies, so that was the triplets, the quads, the quints. These were just the quads and the quints. Now we're focused on one baby. I need to know how many babies there were before I can answer this question. So I'm going to go back to our original calculations here. I know that I have 128,665 twins. Which means times 2 to get the number of babies. I know that I have 7,110, sorry, I had a brain fart there, triplets. Triplets means times 3. I have 468 quads. Quads means times 4. I have 85 quints. Quints means times 5. So I'm going to need to figure that out, and then I'm going to need to add to get the total number of babies. So let's go ahead and grab our calculator and do some math here. So 2,200, 57,000. Why, words are hard today. I'm sorry. I don't know why I'm stuttering all over the place. 7,110 triplets. So 21,330. 468 quads, so times 4 gives us 1,872. And 85 quints gives us 425. So I'm going to go ahead and add those all together. Whoops. And we get 280,957. So a little less than 300,000 babies. I want to know what the likelihood of randomly selecting a triplet baby out of those babies is. So P baby is triplet. I need the number of triplets divided by the number of babies who were part of a multiple birth. So there were 21,330 triplets in that set of babies, and 280,957 total multiple births. And doing that division, we get 0.0759, which is about 7.59%. So if I'm selecting a baby at random, the likelihood the baby is a triplet is 0.759. If I scroll back up, the likelihood that I select a triplet is less than 5%, because 5% was everybody greater than a twin, so a triplet is less than 5%. So looking at counting siblings, sets of siblings, versus counting individual babies changes that likelihood. All right, I'd like to do one more example. There isn't room on this page, so let me insert another page here. Add page. There we go. So we can see what it means when we see some overlap. So we're going to assume that we're drawing cards from a standard deck. So 52 cards, half red, half blue. And I want to know what the probability is that I draw a card that is both red and a 2. Or a 2, sorry, not red and a 2, or a 2. My poor little brain. So what is the probability that I draw a card that is red or a 2? Red or a 2. So or means add. So I know that I'm going to have P red plus P2. And then I need to think, are there any cards in the deck that are both red and 2? And the answer is yes. There are 2 cards in the deck, the 2 of hearts and the 2 of diamonds. Because there's overlap, I have to subtract off those cards that got counted in both. So this time I'm going to do the addition for the 2 individual outcomes, and then I'm going to subtract off their double count, the outcomes that were in both. In all cases, I'm drawing from a deck of 52 cards, so I know my denominator for all of those fractions is 52. Now thinking of the deck of cards, if there's 52 cards, I know half the deck is red, so that's going to be 26 red cards. For 2s, I know there are 4 of each type of card. 4 2s, 4 3s, 4 aces, 4 kings. So there should be 4 2s. And in those countings, I counted the 2 of diamonds and hearts here, and the 2 of diamonds and hearts here. So I need to subtract off those 2 red 2s that got double counted. So 26 plus 40 is 30, minus 2 is going to be 28 out of 52, which gives us 0.5385. Or about 53.85%, which makes sense because we know red by itself is half the deck. Plus, there's an extra 2 cards that aren't red, pushing that percent to be a little bit bigger than 50. Alright, if you have any questions on this video, feel free to send me an email or drop by our Thursday office hours. Otherwise, I'll see you in the next video.